All right, continuing with our catalog of contact forces, the next one we will discuss is a normal force, which we will give a little n with an arrow on top to symbolize. Normal force is not to be mistaken with a common or typical force. Normal in geometry means perpendicular, i.e., at 90 degrees to something, upside down T in math class. And so why do we say perpendicular? Perpendicular to what? Normal forces arise through contact with surfaces. And what they do, why they must exist, is they prevent objects from passing through surfaces. Which most certainly appears to be one of the rules of the reality within which we live. You don't get to just teleport through walls, right? You hit a wall, the wall stops you. There's limits to this, as I've shown in class. For example, you can take a pen, jab it through a paper. You can get it to go through the paper if you break the paper. So there's some kind of limit. Um, but to see how this works, we can go back to our example of the basketball and look at the cases where it was on surfaces. So we had our basketball court, which is flat, and the basketball could be rolling or not rolling. This does not much matter. So we had one where v was equal to 0, and we had one where the basketball was rolling that way, right? So v was that way. And then we also had another one where the ball was on an incline. And we'll look at each of these examples to see how this works. If we take the basketball simply sitting on the court as case number one, well, in this case, we know v is equal to 0. The object is stationary. It's in static equilibrium. Static meaning not moving. Equilibrium having to do with the forces then. And since it's not moving and continuing to not move, the thing we're always after in this next three chapters is it accelerating? And the answer here would be no. And the reason we ask that question is because the answer to that question immediately tells us the answer to the next question. Is there a net force acting on the object? And the answer to that question is no. And now, nonetheless, are there forces acting on the basketball? Well, as we already highlighted, the basketball has mass and therefore has weight, and weight points down. Simple rule for the direction of weight. Well, if that was the only force acting on the basketball, then a net force would exist, and the object would be accelerating, and it would be accelerating down. By virtue of the fact that we know the object is not accelerating, we know there must at least exist one other force that has at least some component that points up. In this case, that other force is the normal force. And the way normal forces work is when you have a contact with a surface, if you can identify the direction of the surface plane, and in this case over here, the surface plane is horizontal, then a normal force will point perpendicular to that surface out of the plane when it's exerted on the object touching that surface. So in this case, the surface is the ground. The object experiencing the normal force is the basketball. The object exerting the normal force is the plane of the ground. Plane of the ground is horizontal, so the normal force will point up because that is perpendicular to the direction of the plane of the surface. In a way we can kind of visualize, and the reason we're going through the forces in the order that we're going, is we can interpret the normal force in terms of the spring force at the micro scale. So if we were to zoom in on the contact between the basketball and the ground, so here's the surface. On this side, it's the ground. And on this side, it's the basketball. And if we zoomed in enough, we could see on the ground that we'd have atoms, right? Stuff is made up of atoms. And in solids, those atoms are locked in position rigidly by bonds. And the way we think of this in physics to a first order approximation is chemical bonds between atoms can be interpreted as if they are springs. And now we see why we talked about the spring force first. With the basketball up here, the basketball will be exerting a downward force, F ball on ground, that's pushing down on the atoms in the ground. That would therefore compress these springs. And what we've already seen for the spring force is when you deform a spring, each of these little springs would create a spring force that points up in response to the deformation. The normal force is nothing more than the combination of all of those little tiny spring forces between all of the atoms when you try to compress them by applying a force perpendicular to a surface. And the rule is that a normal force must point perpendicular to the surface. So in our first case, that was up. However, if we go to this second case of a ball on an incline, we notice that the surface direction is neither vertical nor horizontal. So when we draw our free body diagram, it's very useful then to draw in that diagram a coordinate axis, whether we end up using it or not, that represents the plane of the surface. That surface goes diagonally up and to the right, so that dashed line we might call the x-axis. And then perpendicular to that direction would be the other component direction, which we'll call the y-axis. And so in that situation, we still know that we have weight, and weight still must point down. And weight is still equal to mg. However, the normal force does not point up in this scenario. The normal force has to point perpendicular to the surface plane. Surface plane is the x-axis, and perpendicular to it is the y-axis in this drawing. That means the normal force would point this way. It keeps you from going through the surface. And now what we see, and this is going to happen a lot, is you can end up in situations where you have to deal with multiple components due to the fact that you have vectors that point in different directions that are not collinear. If you were to deal with this in some kind of problem, let's say in this case we knew that the basketball was actually somehow stuck. And that could happen. Maybe you have a lot of friction or something. So if the basketball was stuck in place, then V would be 0 and continuing to be 0. And the fact that V stays 0 means that A would be 0. That means you're in static equilibrium. That would mean that F net would be equal to 0. Just a circumstance, let's say that was true. If that was true, then what I could say is that F net Y would have to equal to 0, and so would F net X, because the only way for a vector to be 0 is if all of its components are 0. Well, this is good because then what I can do is I can decouple my free body diagram into its two components. N is simple, N lies on the y-axis, but the weight lies somewhere between the x and y axes, so I would have to find components for weight. And once I did that, sorry, that should be xy. What I would immediately see is that, yeah, sure, F net Y could equal 0. that could equal 0. That would happen if the size of normal force was equal, sorry, I'm gonna put a semicolon, was equal to the y component of weight. All right, in which case I'd have a vector of equal magnitude pointing up along the y-axis and down along the y-axis, and sure, f net y could be equal to 0. But in this situation, if weight, meaning if the basketball had any mass, in which case it would have some weight, then I would necessarily have some x component of my weight here. And that means that f net could not be 0 in this case unless there existed some other vector, some other force. So f question mark would have to point right along x-axis. And it would have to be equal to wx. We're going to get into what that force could be if it was one singular force in your next catalog entry here for the catalog of forces. That was going to end up being called friction. So that is certainly possible, but that's what it would take. That's how we can figure it out visually.